I hope people are working away on Lab 5. If you've not finished that, Thursday is a good time to wrap that up. It's the week after that, we need to be starting to think about getting Lab 6 worked on. So, get an early start on that. That one will take a while. So if you leave it to the last moment, you'll probably be a little surprised. Okay, so we're in the middle of talking about caches, and our two friends here, Hans and Fritz, are doing 6004 jokes. But there's a lot of truth to what they're saying, which is that in many instances, we sort of need to do some engineering where we have a slow thing that we need to make faster. In our case, our problem is that this main memory system down here, okay, is in fact tends to be slow, and in modern machines it probably has a cycle time that's 1 or 2 orders of magnitude slower than the rate at which we want to run instructions. So it's sort of puzzling that if I have to fetch an instruction every cycle, how do I do that when memory might take 100 cycles to actually return a value? So that's the engineering problem we're trying to solve. And the way we did that is we interposed this yellow box, a cache. And what the cache does, it enables the memory system, think of the cache as, if you will, part of the memory system. Anyway, it's the thing that the CPU talks to when it wants memory data. The cache is able to respond quickly to a certain small number of memory requests. And if we do the engineering correctly, we can parlay the ability to respond quickly to a small number of requests and to a small number of addresses, is what I should have said, to something that will work quite well, because as we observed last time, if we look at over a certain span of time the list of addresses that a program accesses, we'll discover, in fact, that it often is asking for the same address again and again and again. Not right in a row, but if the machine is in a loop, is going to be fetching the instructions that are part of that loop again and again and again, each loop iteration, and there's where the cache can really shine. So what we're going to do today is to a little bit remind ourselves just about sort of the basic functionality of caches, and then we're going to look in detail at a bunch of architectural decisions, which is what us engineers need to actually make when designing the cache circuitry itself. So remember, associated in a cache, this is sometimes referred to as an associative memory, because you address it not by location, okay, but by some part of the contents of that location. People sometimes call it a content addressable memory, because each location in the cache has both an address and then it's remembering the contents of memory at that address. But both the address and the memory contents are remembered, and what we need to be able to do is to quickly, or as quickly as we can, or as inexpensively as we can, that's part of the trade-off we'll talk about today, is to be able to locate a particular address, the contents of a particular address. And so conceptually we search the cache, and we'll talk about how that search works, review how that search works again in just a second. And if we find it, we respond with a hit, and that happens very quickly, sort of on the scale of a single instruction time in the CPU. If we're writing to a memory address, we can simply say, oh, we have that in the cache, I'm just going to update the contents of the cache. However, if we don't find it in the cache, that's a cache miss. And what we need to do then is to go off to main memory. So alpha % of the time, we will hit in the cache. That's called the hit ratio. The rest of the time, which we hope will be only a small percentage, 3 or 4% at most, we'll actually have to go off to main memory. And our goal today is to pick our architectural parameters, turn the knobs as we choose the different sorts of values for how we can do the engineering of the cache, so that we can expect that hit rate to be quite high and that the miss rate is quite low, and then we'll have to go off and fetch. On a miss, everybody has to sort of sit around and wait. Now, we use caches a lot. We happen to be talking about a memory system for a CPU, but for example, your browser uses a cache because it can take a long time to download complex images and web pages from the host, and to the extent that it can, it checks to see do I already have this information? And if so, it will go off and simply fetch the information out of a local copy. That's its cache. And so the first time you look at a web page is often quite slow. In other words, you can actually sort of drum your fingers while waiting for all the images and stuff to load. But often when you come back to the web page, it's almost instantaneous. And that's because almost all of the information, okay, is coming now from the cache. And there's a little bit of a protocol the browser can use to check back with the system. Has anything changed? And if the answer is no, it says, okay, I'm just going to use what's in my cache without having to re-download tens and hundreds of thousands of bytes of images and text. Okay, so caching is your friend, particularly when you're faced with something where there's a long latency that you have to sort of deal with, and what you want to do is to hide the long latency, and whenever you can, do something much, much quicker. So here's the 4 engineering things we're going to be looking at. We'll be looking at associativity, and I'll remind you what that means in just a second. A replacement strategy. So I shall say a little bit more. So associativity is about figuring out how many different places an address can live in the cache. So it could only live in one place, it could live at any line in the cache, and that choice, we can, the more places that live in the cache, the more expensive the search can be. Obviously, if a particular address can only be in one place in a big cache, we only have to look just there. If it can be any place in the cache, we have to invest in the hardware to look everywhere at once, and that's very, very expensive. And so what we're going to be doing is wondering if there's some, first of all, do we need to look at, have a particular address live in more than one location? So we'll talk about why we might want that. And then we'll talk about sort of inexpensive ways to get almost the benefit of having it live anywhere in the cache without paying that expense of that huge parallel search to thousands of locations at the same time. The replacement strategy, so whenever there's a choice of where a value can live in your cache system, now you have, what should I get rid of? If the browser is caching web pages and you go visit a new one and it starts caching information from that new page, what should it throw out? It can't keep remembering all this stuff forever, partly because we run out of local storage, and partly as we remember more and more stuff, finding it becomes more and more expensive, and now, if you have a whole copy of the entire web on your machine, then it's like searching the web, and that's slow. So the idea is to maintain the speed. We want to keep what we have cached reasonably appropriate, and choosing what to throw away is really a question about, well, what are you likely to ask about in the near future, because I'll probably want to keep that. And then I want to throw away things that you'll never ask about again. So we'll talk about that, the engineering of that. There are some ways in which we can take advantage of particular attributes of modern memory systems, which is that they are actually pipelined. They have a long latency, but great throughput. And so the question is, what can we do in the design of our cache to take advantage of a memory system that has a long latency, but a great throughput? And then finally, we'll talk a little bit about the write strategy. When we're doing writes to memory locations, does that mean we have to wait for the slow memory to keep up with us, or are there some other strategies we can pursue? So associativity, first up, top of the lineup. So remember, associativity really has to do with how much searching we're doing. So in a fully associative cache, which you can see over here on the left, what we'll be doing is associated with each piece of data in the cache is of course a tag. That's true in all cache architectures. But we have a separate comparator for each tag. And what that means is an incoming address here could be compared against all the tags in parallel. We're going to search every possible cache location to see if it might contain the address. And that's great, because that, as we'll discover in a moment, that does a great job of solving potential collisions. If there's multiple addresses that might map into the same location in the cache as over here in a direct map cache, they might collide and sort of keep playing bumper cars with each other, kicking the other guy out. Over here, there's no such there's no game of bumper cars. Any location can live anywhere, and so the fully associative cache always has the n most recently used items, okay? Whereas the other caches don't have that. So in a sense, the fully associative caches are gold standard for how well a cache can perform. okay, it turns out to be very expensive. Only a small fraction, a little less than half usually, of the circuitry associated with a fully associative cache is actually devoted to storing the data that we want. So it's an expensive thing. It's also pretty power hungry because there's a lot of circuitry running in parallel here. The other end of the spectrum that we explored last time was a direct mapped cache, in which we use the low order bits of the address to select a particular location in this. So the cache itself actually has a lot of memory associated. Just think of it as a big static RAM that has lots of locations, maybe 1,000 or 16,000 or something. That's sort of the sizes of the caches that you have in your machine. That each hold a data word and a tag, but we're not going to search all of them. In fact, we're going to use the low order bits of the address to select a particular one to look at, and if that happens to be holding the address that we want, we're golden, and if not, it's a miss. We're not going to look anywhere else in the cache. So what we have here now is a very compact system in terms of hardware. It uses these efficient static memory structures quite well, and it has one comparator. The disadvantage is, of course, we're only looking in one place, which is, as we'll see in a moment, gets into trouble. Do people remember why we use the lower order bits of the address to determine where to look in the cache? Yes? Right, so our locality of reference is really saying it's the low order bits of the address that are changing. Right, the notion is, like as you were pointing out, the example of a program counter, as it goes through a loop, and when we look at the addresses of the instruction, those addresses differ in their low order bits. And so what we want to do, for example, is hopefully all the instructions of a loop would fit into a cache. So by using the low order bits to determine where to look in the cache, what we're doing is we're taking things that are most likely to be referenced in short periods of time and making sure that our mapping function between the address and the cache location spreads those out into different cache locations. Okay, so that's why we use the low order bits. And then, of course, what we're doing is we store the high order bits of the address, okay, of a memory location in the tag, and we compare that with what the high order bits of what's being asked for. So a combination of what line we're looking in and then the tag comparison will basically do the address match for us, but we're only checking in one place. Okay, so we're checking everywhere or we're checking only once. And I hope everybody can sort of understand that there's a middle ground here, which is maybe you could check in 3 or 4 places. And so we're going to sort of explore that middle ground now. So first, let me just start off by pointing out the problem with direct map caches. Here what we have is a little program loop. It's running at word address 1024, so you can see a little 3-instruction loop that just repeats again and again and again. It's going off and accessing some amount of data that's stored, in this case, at word 37. And you can see that these addresses, when we figure out where they live in the cache, live in different parts of the cache. So just to remind ourselves once again, how would I take a word address and decide where it is in the cache? Well, we have a 1024 location cache. So what I'm asking is, I got a 32-bit address from the beta. Since we're dealing in word addresses, I'm going to leave off the bottom 2 bits. Okay, what address bits do we use to access the direct map cache? The low order bits. And how many of them? Because we have a 1024 location cache. 1024, it's 2 to the 10th. By the time, I'm sorry? Yes, the 10, so these 10 bits right here, okay, are the index into the cache. So what we really want to do is to take the word address mod 1024, right? And so that's why address 1024 maps to cache line 0, and address 1025 maps to cache line 1. So this is more than academic. We're going to spend some time, certainly you're going to be responsible for figuring out, if I do run this little loop, how well will it work on a particular type of cache. What you need to do is to turn the addresses the CPU generates into figuring out which cache lines will be accessed. So you have to understand this address mapping to cache line, or this address to cache line mapping, in enough detail to be able to figure out what cache line an access is going to. So that's what we've done here. And they all come to different cache lines, so they could all potentially be hits. However, if I change the data location, if I somehow, you've edited the program, you've added a couple more arrays that have nothing to do with this loop, but you've moved where what used to be at 37 is now at location 2048. Okay, you didn't think you changed anything, but the addresses of where data were being stored changed, and now you can see that your program will actually run horribly. Instead of actually being all hits, you can see that when I fetch, I do an address, maybe in fairness I should have written hit here, or at least maybe for the first time. But location, the data location where I'm fetched, so the instructions are coming from the thousands range and the data's in the 2000s range. When I access that first piece of data at word address 2048, what happens? It gets mapped to cache line 0, right? We're taking the address, the word address is mod 1024 because we have a 1024 location cache. So now what we discover is that some of the data and some of the instructions are colliding in the cache. In our direct map cache, we have two locations that are being mapped to the same cache line, and only one of them can live there. And if I'm in a loop, you can see what's going to happen is they're going to play bumper cars all the time. The data will push out the instruction will put out the data. So every time we look, what we want, so we have a pattern that goes instruction data, instruction data, instruction data, instruction data. Every time I'm doing this, unfortunately, I'm kicking out the stupid, I'm kicking out the guy I'm going to want next. Okay, so this is what's called a collision problem. The addresses are colliding, in other words, they're mapping to the same cache line, and we're not finding anything in the cache. Now, if you want to amuse yourself, you can Google around and you can actually find programs that have been designed to break the Intel caches. In other words, they're designed to produce nothing but collisions in your caches. And your fantastic 2 gigahertz machine that you're so proud of actually turns into a couple hundred kilohertz machine because the caches are no longer working. Right? They're actually, now it turns out, as we'll see, Intel, like we're going to describe, actually has a more sophisticated cache architecture other than direct mapping. But if you break the cache, if there's some access pattern that causes the cache to perform poorly, your machine suddenly turns into a very, very, very slow machine. It's like going back in time 3 decades, in terms of performance. So it's quite remarkable. So you Google around, run one at home, and sort of go, my God, I didn't know anything that this simple could run this slowly on a modern machine. But now you know why. Okay, so here's our two choices. We have fully associative versus direct map, just sort of a listing of comparisons. Speaking of comparisons, the number of comparators differs. So this search is very highly parallel in the fully associative system. This search only looks in one place. And the replacement strategy, in other words, what to throw away, well, every time we bring something into a fully associative cache that can live anywhere, we have to pick where it should live. And so we throw away the least recently used item. In a direct map cache, there is no replacement strategy, right? Because it can only live in one location. For a particular address, I can perform the same mapping that the cache will perform and so identify the cache line it will live in. And so, given a choice of, where's this going to, address 37, where's it going to go in the cache, it's only going to go in one place. So that's the location that will be replaced. Okay. So the real problems one is highly expensive but very effective in terms of implementing the functionality of a cache. Much more efficient from in terms of hardware and cost and power and speed even. Is the direct map cache, but it has the problem of contention. So what are we going to do? Was that a question or a almost question or metastable question? Okay. Okay. So if we make caches bigger and bigger and bigger, the chances of contention go down because we have many more cache lines to map the addresses. And so what we hope is that by spreading out we're going to spread out the information over a larger cache, and so the chances of any two things colliding get somewhat smaller. So we'll discover that we'll want to build large caches, and that's always a good first step. Given a choice about what architectural parameter to adjust in the cache, consider making it larger. That's always a good thing. And in fact, I'm going to pull a number off my head. 80–90% of the transistors you buy from Intel are transistors devoted to big caches. And then you happen to buy a little CPU. But the reason that, it doesn't make any sense to have a CPU that can execute instructions, a bazillion times faster than the cache and memory system can deliver them on the average. So it's getting that ratio right that you pay for when you buy many cache transistors. Okay. Remember this diagram here when we were talking about locality of reference? And we sort of identified we're fetching, program, some information from a program, and there's a lot of locality there. We're fetching information from a stack frame. We're perhaps dealing with data structures or pieces of arrays here. If we think about how many different hotspots there are, there's not an arbitrary number of them. It turns out there's only 3 or 4 or 8 or 6 or something, but a handful of hotspots that over several hundred instructions that most programs will be accessing. They'll be accessing the hotspots a lot of accesses to the stack frame, a lot of accesses to the instruction in the loop. But there's only, and if each one of these can be located at a different place in memory, they have the possibility of colliding. But there's only, in a sense, sort of 5 or 6 collision possibilities that we have to deal with here, right? Because we have to worry about the data colliding with the stack, colliding with the program. But those there's a certain locality and coherency to each of those separate address regions. And so what we're going to do is design our cache to take advantage of this small number of hotspots. Okay, instead of having a direct map cache, we like the direct map cache because they're sort of simple. What we're going to do is to make a collection of n direct map caches. Okay, so instead of having a single location at which a particular address can be cached, we're going to have a set of locations. One element of the set comes from each of the n caches. So these things are called n-way set associative caches. Okay, so they look like this. And I hope you can certainly realize that this is just a picture of a direct map cache. But instead of having, a fully associative cache, which you can think of as a single, as a single line, we're going to have, a fairly substantial direct map cache, but we're going to have n copies. And one of the things we need to talk about, what should n be? 2, 4, 8, 32, 128? I mean, what's the right number? Okay, so let's talk a little bit about that. But everybody just sort of see this picture here. These are n, and the picture here shows 3 almost. And although there's no particular reason that there should be a power of 2, they almost always are a power of 2. So 2 or 4 or 8-way caches. These are n direct map caches operating in parallel. They're each checking to see whether that particular cache line, the one that's indexed by the lower order address, happens to hold the contents of this entire, of the memory location the CPU is trying to access. So here's some questions. Is it possible for a location to be nowhere in the cache? Of course. I mean, the memory system hasn't loaded it. Okay, we expect it to be, hopefully it will be in one location in the cache. In a system like this, would you ever expect to find a memory location cached in more than one of the subcaches, of the direct map subcaches? In other words, could a particular memory location appear more than once? Well, there's 2 ways to answer that. One is it would be sort of silly. It would be a waste of resources if it appeared more than once. It's a little unclear what this hardware would do. Okay, if they said, this guy said, I have a hit and turned on his drivers for his data line, and this guy says, I have a hit and turned on his drivers. It would be even worse if they sort of were remembering different values, right? So in general, all caches are designed to hold each location 0 times or 1 time, but not more than 1 time. So the goal will be to actually have this act like a very big cache. In other words, this particular guy can have, well, I'll just literally look at this picture, 3 times n locations, or 3 is n, excuse me, 3 times 2 to the t locations in the cache. So it has a lot of locations. It's just divided up so that we're using the direct map technology to figure out where to look. Everybody sort of get that? This is not a complicated picture. Yes, sir?
Just to make sure, each yellow thing is direct map cache.
Each one of these columns is a direct map cache.
So the T were not go to each of them in parallel.
So we're doing, in this case, n possible searches in parallel. We're not searching the entire cache in parallel. We're searching n where n is 2 or 4 or 8, depending on the number of direct map caches we're doing. So we're getting some amount of parallel search. And what we're going to find when we look at some performance graphs is by the time we get to about an 8-way set associative cache, it's as good as a fully associative cache almost always. Okay, so the terminology, just to be clear, is that a cache line is in a particular one of these direct map caches. It has a tag and some data. And then there's a set of cache lines where each element of the set is coming from a different direct map cache. So when I talk about a set associative cache, the set I'm referring to is the set of locations that a particular address can appear in. And it will appear in at most one of them. At most one of them. Okay, so the numerology of caches, you should sort of look at this slide and sort of figure it out, right? I mean, what would it mean to be a fully associative cache? I mean, that's like setting t to 0. What would it be like to be a direct map cache? That's like setting n to 1, so forth and so on. So the entire space of cache architectures are sort of described, along these axes, and exactly which place along these two axes you should choose. This is now we're back to figuring out, on the average, we want our machine to perform well. Okay, so what we need to do is to spend a little bit of time thinking about how to perform well. Okay, so the first thing I want to talk about here now is if I have an associative, so in both the n-way set associative and the fully associative caches, okay, I know there's a slide coming, and I'm just making sure I knew where it was. Okay, so in an n-way set associative cache or in a fully associative cache, we do have this problem where once something is, I need to bring a new thing into a cache and I need to replace something else. How do I make that choice? Okay, so we have a replacement strategy issue, so we'll talk briefly about that. So here are some choices. LRU, least recently used. That's the one that makes most intuitive sense when you think about how a cache is trying to work. It's trying to remember the things that you're likely to use. If by locality, meaning that you're more likely to use things that you've recently used and less likely to use things that you haven't looked at in a while. And in fact, there's a sort of notion that at some point I'm going to stop accessing things altogether, and those are the ones I'd really like to throw away. And given that I don't have, my only indication about the future is often the past. In other words, what have you been looking at? You're in the middle of this loop. I'm going to guess you're going to go through that loop again. Okay, and so what we're going to do is to keep the most recently used items in the cache, and so the replacement strategy is the goal of finding the least recently used. So for example, if I have a list here that sort of keeps track of the cache locations, in this case, cache lines, here are the different, in this case, a 4-way set associative cache, and set 0 had the most recently used item 1, 2, and 3. And I do a memory access that hits in the second set of my 4-way cache. It hits in 2, so 0, 1, 2, and 3 are the 4 sets. What we're going to do is just remember that that was now the most recently used. So it gets moved to the front of the list. And then as I go through and I imagine a series of hits and misses, you can see I'm reorganizing that list to keep track in order of what's the most recently used, the next most recently used, so forth and so on. So in order to implement a LRU strategy in an n-way cache, I actually have to keep this list of n items in order, which set was the most recently used, so forth, which element of the set was most recently used. This is expensive because there's n factorial possible orderings. And so if I have to, what's the state representation of something that has n factorial choices? Well, I'm going to take log base 2 of that to figure out how to encode that in bits, and then I can sort of do some fooling around. This is very expensive. It actually becomes, this is a complicated piece of hardware to build. And so mostly people don't build true LRU caches. They're just too expensive. the memory and the state transitions required to build an FSM that controls an n-way set associative cache, where n is, say large, like 8 or 16, becomes that hardware becomes almost as complex as the cache itself. Okay, how about FIFO, or least recently used? In other words, I'm just going to take the oldest thing. That turns out to be really cheap, because you just keep one pointer that points, think of, I have an array of things, 1, 2, 3, 4 things. I have a pointer that points to the oldest one. If I need to replace something, I simply retake the oldest one and replace it with the new stuff, and I just move my pointer forward 1. So I'm just going to keep my things sort of in cyclic order here in terms of age, and I just keep track of where I am in the cycle. So FIFO is very simple to implement in hardware. The trouble is it doesn't have very good cache performance. Okay, so it's cheap, okay, but it doesn't perform very well. It often has the attribute of throwing away, it makes bad choices about what to throw away. Because often the thing that you accessed least recently in terms of, is the thing that was brought into the cache the longest time ago might be the thing you're about ready to access again. Right, because you're going back to the top of the loop. So the idea of most recent access is a better measure of how frequently you're going to be using it than how long ago did you bring it in. So the age of something doesn't really give you a good sense of its level of activity, and it's the level of activity that's most important in caches. On the other hand, why do drunks look under streetlights for their keys? Because that's where the light is. It's the easiest thing to do. Well, that's the same reason why people sometimes implement FIFO strategies. How about random? Why would random be interesting at all? Yes?
There are no single cases we can point to where it's bad. Well, I guess it says there.
Right. Right, so random is neither good nor bad, and depending on whether your cups are half full or half empty in life, it's very hard to write a program that makes a random cache perform poorly, because you can't outguess it, because it's making a random choice about what to place. And most of the time, it will not be throwing away the thing that you want left, you want next. So it will make, it's an interesting choice that randomness can be your friend in a situation where you're a little muddled about the actual statistics of the access. In other words, it prevents pathological behaviors. It turns out that it's actually very inexpensive to implement because you're generating a random number. You just need some sort of pseudo-random number generator using some sort of linear feedback shift register. That's how most of these things are built. And you can come up with pseudo-random sequences that have that cycle through numbers only once every many days, accessing them a billion times a second, right? So you can build things that are pretty effectively random with only a small amount of hardware. So random will actually be an interesting choice particularly if you're worried about poor performance. Okay, LRU is best, for instance, if you only have a two-way set associative cache. And in fact, LRU is not very expensive to implement then. So I would always implement LRU if I can. But if I had a restriction on if I had 4 or 8 or 16 things to keep track of, LRU would be too expensive. And then I'd probably implement random because it would perform almost as well. And I would almost never choose FIFO. Yes? Well, what happened here is because we had a miss, we don't know what was being accessed. 3 was the cache set, the element of the cache line that was least recently used. So that was the one that got replaced. And so now that I've replaced it, is now the most recently used. Does that make sense? So this red thing is trying to just imply that the contents of that cache line actually changed. Okay, and since that was the one we chose to put the new value into when we brought it in from the memory system into cache line 3. And so what we did, or into element 3 of the set of caches. And so now that becomes the most recently used among its neighbors. Does that make sense? Okay. Okay, so let's think a little bit about how do we talk about cache performance. And this is something that you'll be expected to do. What we're going to do is we're going to run we'll give you a program and say what's the hit rate of this program running on that cache? Two-way set associative, 512 lines, LRU replacement strategy. And you sort of go, whoa, that's a lot to ask, Chris. How do I figure this out? And the way you do it is, first of all, you should probably start by figuring out the sequence of addresses that will be accessed. So almost always we give you little loops, right? So this tends to be a repeating sequence of addresses. And we actually turn what we call a reference string. We don't really care about the program. From the cache's point of view, it knows nothing about the semantics of the program. It just knows about the sequence of addresses the CPU is asking for. And then we basically turn those from byte addresses back into word addresses. And those we map into which cache line. And so what we're trying to do in the end is figure out what's the sequence of cache lines being accessed by the program. And from that we can determine the hit rates and things like that. So, for example, here is a very simple program that is a little instruction loop, goes 100, 101, 102, 100, 101, 102. So those are the program accesses. And then it's accessing data. So it's accessing data at 1,000, and the next time through the loop it accesses at 1,001. These are word addresses. Now, in a fully associative cache, how do we do the mapping to cache line? What portion of the address are we using to select where to look in the cache? This is a trick question. Yeah, so fully associative cache, we actually are going to look everywhere in the cache, right? So remember when I said a fully associative cache, t as in 2 to the t was 0, right? So in some sense, where a thing lives in the fully associative cache is completely determined at the moment I brought it into the cache. What was the least recently used location? That's the cache line it's going to live in. So the cache line that you live in a fully associated cache is unrelated to the address, right? It only related to the history of the previous accesses, right? And what we can see here, just to say a little bit more about, so we always have this notion of compulsory misses. Those are the first time you access a location, of course it's not going to be in the cache. We haven't fetched it yet. Okay, so usually at the beginning of a program, there's a certain number of compulsory misses. Typically, we're not interested in that in the performance of the cache, the steady state behavior. In theory, the loop will happen so many times that the fact that we missed everything in the first time of the loop won't matter. But what we discover is that as we bring in the data words one by one, notice that they replace each other in the cache. Right? The program, at the moment that we're bringing in a data word, okay, it turns out that the 3 instructions in the loop were always the most recently used items. The thing that's least recently used is the previous data word. Sort of makes sense, right? We're going through, and at some point in this 3 instruction loop, we're fetching some data, and it turns out the least recently used item in the cache at that point was the data fetched from the previous time in the loop, because we've touched all the other instructions since then. Right, so those, we can see that in this case, we sort of have a series of compulsory misses. So we actually have about a 25% miss rate, or a 75% hit rate in the fully associative cache. In the direct map cache, you can see we do much worse than that, right? For a while, the data addresses and the instruction addresses are mapping to the same cache line, which causes them to throw each other out. Right? So we see a lot more misses early on. Once we get to the point where the addresses, okay, are not colliding so badly with the instructions, we do a little bit better. Okay, but this one has about a 50% hit rate, or miss rate, being sort of what you'd expect. Okay, so does that sort of make sense? So here's an example of a direct map cache where some of the data accesses are colliding with some of the instruction accesses, and so what happens is that the data replaces an instruction we're going to want later in the cache. So LRU isn't saving our bacon here. It's being, the LRU effect is sort of well, we don't have a replacement strategy, I'm sorry, in a direct map cache. Now we go to an n-way set associative cache. Here's a fully associative cache. Here's a 2-way 8-line total, so 4 cache lines in each of the 2 sub-caches. And we do the same sort of program. We discover that, in fact, that the 2-way cache is doing quite well. And in fact, it performs exactly the same, okay, as before. Now, why does the two-way cache perform, why would you expect the two-way cache to perform well? This is sort of the essence of why n-way set associative is a good idea. What do you think? Well, why did the direct map cache perform less than well? Let's start with that question. Yeah, go ahead.
Because you have your data addresses and your instruction addresses and 1,000 and 100 are colliding, but then you have two places to put those while you're looking at is 1,000 and 1,000.
Right. So the answer to why direct map caches aren't performing well is always, there must be a collision problem. Right? And so now you go look to see what the collision problem is, and it's the fact that the data and the addresses are competing or colliding for the same cache lines. Okay. In this particular very simple program, how many different sort of address streams are we talking about? They're interleaved, but there's the instruction address stream and the data address stream. And those are sort of two independent streams, right? And it's the fact that they interleave and collide that causes us a problem. Right, and so it turns out with only two ways a set associative cache, if it's possible for now two addresses to map to the same cache line, because we have now two sub-cache lines where they could both live simultaneously, we discover that the two-way associative cache with this very simple program performs exactly as well as a fully associative cache, because there's really just an instruction stream and a data stream. So if you think about n-way set associative, the question you really want to ask yourself is, how many different address streams are there? Can I break them into a small number of buckets? You know, data 1, data 2, you know, instruction. You know, am I copying from one array to another? So I'm sort of thinking about the instruction, this loop that's doing the copying, you know, array 1 and array 2. And if they can all live in the cache together, then I'm going to have a pretty good hit rate. Okay. So if we talk about the associativity and the hit rate, this is a chart that's worth looking at because it sort of gets at the essence of cache design. Right? One thing you notice is that in general, having more memory, having more cache lines is better than having fewer cache lines. See, all these guys are dropping dramatically, right? And so, so making the cache bigger is almost always better, okay, than adding ways of associativity after a certain point. So what you'll notice here is that an 8-way cache, this line that's just above the fully associative, so the best you can do is down here. So this is potential measurements of a particular benchmark. You notice that the 8-way cache performs almost as well as a fully associative cache. Does that intuitively make sense? At this point, you should all be bobbing your head sort of yes, because if you think about how most programs work, there's not that many, remember that little dot diagram? There were not that many different regions of the address space that we were accessing at any given moment. The program, the stack, a couple of the data regions, right? And so it's easy to sort of, depending on how complicated the data accesses are, you can get up to 2 or 4, I mean up to about 4 pretty easily. And the extra associativity accounts for more complicated behavior about accessing several different data structures at the same time. But after that, you can put a lot more money into the cache hardware and it won't be any better. Okay, what do you own? Most of you own I forget what it is, 4 8-way, 16K line cache, something like that. That's your level 1 cache on your Intel processors. Now, your Intel processors actually have 3 levels of caches, okay, where each level of cache is about a factor of 2 slower than the previous level. And so this cache here is a multi-way cache. The bigger caches tend to be more like direct map caches. Okay, any sort of? Okay, so the goal is to make a processor where what you're doing is getting the miss rate down. What do we want the miss rate to be? Well, we'd like it to be 0. We're never going to quite get there. But remember the arithmetic about computing the average access time? Right? We figure, miss rates in the 5% range, we're looking okay. That would, if I had a 4 nanosecond cache and a 40 nanosecond main memory, a factor of 10, I could get something that had a 5 nanosecond access time if I had a hit rate of 95% or a miss rate of only 5%. So we sort of want to be down in this region of the cache. And if we're not, we start really seeing the slowness of main memory. Now, it's always possible when we're dealing with replacement strategies, you can say, well, is LRU always better? So I'm here to warn you that the word always in the question about caches is almost never true. In other words, a cache can be better. For example, a direct map cache, a bigger direct map cache is always better than a smaller direct map cache. It holds the same information. It's better. But typically when you have two-way versus direct map, FIFO versus LRU, you can always come up with a program that shows one to be better than the other. So if you see a quiz question that uses the word always, approach that with caution. You have to really convince yourself that if this cache are exactly the same except one is bigger, I mean literally bigger, it has more cache lines, but the architecture is the same, then you can safely use always. Other than that, you almost certainly can write a program to distinguish between the performances. And so, for example, this little example is using an LRU versus a FIFO replacement strategy. What we're doing is look at this sequence of addresses, and what we're trying to do is to come up with a sequence of addresses that put different items into the two different caches. So when you go home and think about this later, is this sequence of 4 addresses in an LRU cache after the 4th access, this is what's in the cache, and after the FIFO, in a FIFO cache, those are the 2 locations in the cache. And now I can make whichever one of these I want to win simply by asking for the location that the other one doesn't have. You sort of get the strategy for sort of proving caches not as good or another. So what I'm trying to point out here is more make the observation that there is no one winning strategy except usually size. If you don't change the architecture but make it bigger, typically it performs better. Other than that, I can always find ways in which one thing performs better than the other. A very simple thing to do with an architecture of the cache is instead of having a single data word, have some power of 2 number of data words. So I can have, in this case, a 4-word block associated with each tag. I'm going to use now I'm going to replace this picture here with sort of B bits here, which will determine which word of the block I'm trying to access. Okay, and then this is the cache index, like so. So now I'm using the address in a slightly different way. I'm still using some field of it here to select which cache line to look in my n-way set associative cache. But I'm going to use a small number of these bits. In the case of a 4-word block, I'd be using 2 of them, okay, to amortize the cost of the tag over a bigger amount of data. Block caches are actually really neat. Why? Because when you think about how instructions work, if I'm going to execute the instruction that's in that location, with high likelihood, where's the next instruction going to live? At PC plus 4. So you can imagine that caches that are block caches are particularly good at instructions. I'm not increasing the amount of tag hardware or anything. All I'm really doing is making it so that if I'm going to access one element in a block of data, I'm likely to access the next element. So for small block sizes like 4 or 8, that's pretty good. You can't take this too far. If you make the block be 2 to the 16th words, now, chances are you'll be, put a lot of energy to bringing all those words in, okay, into the cache, and then only access a small portion of them. But for small blocks, it's usually the case that the cost to bring them in will be paid back because you'll almost certainly be accessing them. Okay, now remember that because of the way this cache is organized, if one word in the block is there, all the words have to be there. In other words, remember the tag isn't telling me which pieces of the data are there. The tag is either says it's all here or it's all not. So I'm going to pay the cost of bringing in 4 words and hope that it's paid back. Okay, so the other thing that's nice about this, in a memory system that has a high latency but a good throughput, is that we have to pay a lot to get that first word, but the next words will come a very small number of nanoseconds later because of the pipeline nature of the memory system. So we're able to bring in a lot of different words in a row here very quickly. So typically we have a wide path from memory, and then we can use the pipeline nature of our synchronous DRAMs or DDR RAMs to actually fill up words very quickly. Yes?
So I'm not trying to understand what exactly the blocking is.
The blocking is basically saying instead of having only one data word for the tag, I'm going to have 4 or 8 or 16 data words per tag.
So the tag, instead of identifying, are you just like...
The tag is still identifying the address of each of those locations. It's just that it's identifying the address of a block of, in this case, 4 locations. Okay. So,
it's going to like ignore the lower several other bits.
right. So there are some bits that are going to be of the address that are now being used to select the word within the block. And the address of the block now has correspondingly fewer bits in it. You get a sense by looking at this picture of how the addresses in the blocks go. So everything is blocked, right? So nowadays we have 4 and 16 word blocks, but not much bigger than that. Okay, I'm going to stop here. We have some questions about valid bits and the write-back strategy, which we'll cover in section. So good luck in finishing Lab 5, and we'll see you Thursday in lecture.